Welcome to Spring LIB.
Is angular momentum of the block conserved? So, since we have no force on the particle that's towards the center, then that means the net torque on the particle is 0, and so yes, angular momentum will be conserved for our problem. Now moving to B, what's the new angular speed? We can apply our expression I1 omega 1 is equal to I2 omega 2. And so omega 2 is equal to omega 1 times radius 1 over radius 2 squared. We have our 1.95 times our value of our distance, 0.3, over 0.150 squared. And then we plug this into a calculator to find our new angular speed. So 0.3 over 0.15 squared, we get 7.8 radians per second for part B. For C, find the change in kinetic energy. Now let's first find our initial kinetic energy. That's going to be 1/2 I1 omega 1 squared. So it's the same as 1/2 mass radius 1 squared times omega 1 squared. We plug in 1/2 times our mass as 2.4 times 10 to the negative 2 times 0.3 squared times 1.95 squared, and we plug this into a calculator. So 1/2, 2.4 times 10 to the negative 2 times 0.3 squared times 1.95 squared. We get 0.004 joules as our initial kinetic energy. So let's not circle that, but let's just underline that. Now we want to find our final kinetic energy, K final. That's going to be 1/2 mass radius 2 squared omega, that was going to be omega 2 squared. So we plug in 1/2, 2.4 times 10 to the negative 2 squared times our 0.15 squared times 7.8 squared to get 3.94 times 10 to the negative 4 joules. Now, our change in kinetic energy is just K final minus K initial. So 3.94 times 10 to the negative 4 minus 0.004. We end up getting a value here of and we end up getting a value of 0.003 joules as our change in kinetic energy. Now we'd like to find, for D, how much work was done. The work is just equal to our change in kinetic energy of 0.003 joules.